Okay, so in the previous video, we looked a little bit about approximating, giving a subspace, given a vector in Rn and a subspace V of Rn, how can we best approximate B using only vectors in that subspace V? And when I said approximate, I said with respect to some norm induced by an inner product. Okay, so depending on how we're going to measure things in Rn is going to tell us which inner product we're going to want to use. And some of you may be taking other linear algebra classes, either now or in your past education. You might have thought, why would we ever want to use something other than the standard inner product on Rn to be able to measure distances and angles and stuff like that? Well, we're going to see some examples coming up why there might be other metrics and other inner products that we want to use in the context of iterative methods, and that's just one context. There's a lot of other times where you might want to adjust the standard distance and angles and sort of things in Rn. Okay, so I want to again go back to sort of thinking about this as solving a problem like Maria. I mean, mx is equal to b. You want to think about solving a problem, mx is equal to b. So why am I putting in this context? In our context, m is not always going to be the matrix A that we're trying to solve. So in our context, we're going to have ax is equal to b, and that's sort of the ultimate goal for what we want to solve. But there's going to be intermediate steps, and this matrix M, it could be A, or it could be other matrices related to A. So I just want to look, sort of step back, think through things just a little more abstractly than just being directly related to this class, and I want to think about solving this equation mx is equal to b. Now, we saw that we can kind of, we can sort of replace this equation with the following. Minimize mx minus b. So find the x that minimizes mx minus b. So just a refresher, why can we do this? Well, if this problem has a solution, then it's going to be there's going to be a vector x so that mx is equal to b. In other words, mx minus b is going to be equal to 0. And 0 in any vector, the 0 vector in any vector norm is equal to 0. And furthermore, only the 0 vector is equal to 0. So, only the 0 vector has norm equal to 0. Okay, so what this tells us then is if this problem has a solution, this procedure here, minimizing, finding the x that minimizes mx minus b is also going to give us the solution. On the other hand, the reason that we really like this is because if mx equals b doesn't have a solution, this is going to give us the x that gives us the best solution, where best means minimizes the residual mx minus b according to some norm induced by some inner product. Okay, so another way to state this problem is find the vector. I'm going to call it v. And again, I think we went over this in the previous video. In the column space of A, I'm getting new chalk tomorrow. Got one tiny little piece of white chalk here left. And I'm not going to use the Crayola chalk. So, okay. Find V in the column space of A that minimizes V minus B. Right, because as x ranges through its space, m times x is going to range through the column space of A. And so we can replace v with m times x. Okay. So make sure you understand that, because it's something that's going to come up a few times. Okay, well, we saw in the previous video what this means is find a vector v in the column space of m, which I'm just going to abbreviate as column of m, such that v minus b is orthogonal to the column space of M. So we want to find a vector v so that v minus b is orthogonal to the column space of M. We saw that in the previous video, but all we're doing is we can write b as, for any vector b in any subspace, we can write it as something in that subspace plus something orthogonal to that subspace. And we want v to be that, the something in that subspace. And then so v minus b, we're taking v, we're subtracting off the part of, we're doing v minus b. Actually, it might even look a little bit cleaner if I write it equivalently as b minus v. Okay, so we're taking b, we're subtracting off from b the part of b that is in the subspace, and so the only part that's left is going to be the part that's orthogonal to the subspace. So if I just explain that one more time, any vector, including b, can be written as something in the column space of M plus something orthogonal to the column space of M. V is going to be that part of b that is in the column space of M. And so what we're doing then, b is written as something in the column space of M plus something orthogonal to the column space of M. V is that part that's in the column space of M, so when we do b minus v, we're taking b and subtracting off the part of b that is in the column space of M, and so the only thing left is the part that is orthogonal to the column space of M. Okay, and the sort of the formality of this was all done in the previous video. Okay, so what have we done? Solving this. If we can't solve this, we can solve this minimization problem. This minimization problem is the same as this minimization problem, and this minimization problem is the same as finding a v in the column space of M, so that b minus v is orthogonal to the column space of M. Okay, so what does that mean? What does b minus v being orthogonal to the column space of M means? Well, it means that b minus v, if we do the inner product of b minus v with the column of M, this is equal to 0 for all columns M of the matrix M. Okay, the columns of M, by definition, form a spanning set for the column space of M. So in other words, all of the columns of M are in the column space of M. So if b minus v is orthogonal to the column space of M, it means all of these inner products have to be equal to 0. On the other hand, if we know all of these inner products are equal to 0, and we take any vector in the column space of M, we can write it as a linear combination of the columns of M, then it means that if this is true for all columns of M, then actually this is true for all, not just all columns of M, but for all vectors in the column space of M by linearity. Okay, so let me just explain that briefly. Indeed, if I'll call it W is in the column space of M, I'm not going to write that because I'm going to run out of room. So if W, actually I can't. So if the W is in the column space of M, then W is going to be equal to the sum k equals 1. I'll call it L. We'll say that M has n rows and L columns. Okay, k equals 1 to L AK MK, where MK is the kth row of M. Okay, so then I want to show that if this inner product is equal to 0 for all columns of M, then B minus V times W, or the inner product of B minus V with W is equal to 0. Okay, but this is just a simple exercise using the linearity of the inner product. So I'm going to replace W with that sum, and it's going to be this. The sum k equals 1 to L AK B minus V MK. But MK is a column of M, and if B minus V is orthogonal to M for all the columns of M, then all of these inner products are all going to be equal to 0. These are all equal to 0. And so if we're adding up 0 L times, overall this will be equal to 0. Okay. All right, so then the solution to this minimization problem, again, is going to be the V in the column space of M such that B minus V is orthogonal to all the columns of M. Okay. Now, another way that we can write this, okay, we can kind of go back to this formulation here. Remember V, the reason we're talking about V being in the column space of M is because that's just M minus X. So really what we want to do is find an X so that B minus MX, that inner product is equal to 0 for all columns M of M. Okay. I'm gonna have to switch chalk here because I'm about to scrape my fingers on the chalkboard. Okay. So I'm actually going to now replace this with MX because I need the board space. Okay. All right. So actually, let me make this look a little cleaner. Minus M X. Okay. So now I need to explain a little bit something about inner products, because what I want to do is I want to relate this to a. I want to now take this and put it back into a matrix vector equation that is guaranteed to have a solution. So first, I'm just going to show this. Assume that the inner product is the standard dot product. Okay, so let's just look at this case, and then I'm going to show you how we can modify this to make it work for when this isn't the case. Because remember, we need to do this in different generality. Okay, so assume that that is a standard dot product. Then what does this mean right here? Well, let's think about this. B minus mx is a vector. We're doing the product with the column of M. That's a vector, and it's equal to 0. So let's see if you agree with this. So this is equal to, this dot product equals 0 for all columns of M, if and only if we look at M transpose times B minus mx, this is equal to the 0 vector. So I'm saying this statement and this statement are the same. So pause for a moment and see if you can figure out why. Okay, so why am I saying that this is the same? Well, what are we doing when we do M transpose times this vector right here? Well, M transpose is just the rows of M transpose are the columns of M. So if I look at the first entry of this output vector here, it's going to be equal to the dot product of the first row of M transpose with this vector right here. But the dot product of the first row of M transpose is just the dot product with the first column of M. And we're saying that is equal to 0. So what this says is the dot product, what I just said is that the dot product of B minus mx with the first column of M is equal to 0. We go to the second entry. This says that the dot product of the second column of M with this vector is equal to 0, and so on and so forth. So this statement is equivalent to this statement under the assumption that we're dealing with a standard inner product. Okay. And if we're dealing with the standard inner product, then we have this. This is now a matrix vector equation that we can write as M transpose mx is equal to M transpose B. And because of all of the theory that we've put into this, this is guaranteed to have a solution. Okay, now we're not saying it's guaranteed to have a unique solution, but this is guaranteed to have a solution. And so now, matrix vector problems are nice to solve because there's algorithms for solving them, but we can't always solve them. So now we have replaced a minimization problem, which seems more challenging, with an equivalent matrix vector problem. Okay, so now let's imagine that we no longer have this standard inner product. Okay, so what happens in this case? Okay, I'm going to try a different color here. Bear with me, please. This color might be a little crazy. We're going to see how it looks, though. Okay. So we're going to look what in the case. What about if we don't have a standard inner product? Okay. So my claim. Okay. Maybe not. You know what? It's not so bad. Claim if xy is an inner product, there exists a symmetric positive definite matrix G such that this inner product gxy is equal to the standard dot product of gx times y, like that. That's my claim. That any inner product on Rn we can really write as a sort of oblique dot product, gx dotted with y, for some positive semi-definite matrix, or sorry, some symmetric positive definite matrix G. Okay, so write that down, and I'm going to prove this. Okay, so the first thing that's not really necessarily a proof of this, it's not really part of the proof of this, is to prove that if you define some inner product in this way, xy as equaling xy as equaling the dot product of gx with y, that this actually defines an inner product. Okay, so how can we verify this? Well, remember, a way to think about this is simply to think about this as gx transpose times y, where we're doing like transpose here. Now we're doing like matrix vector multiplication. Okay, because what's going to happen, g times x is going to be, the output is going to be an n by 1 vector. We take the transpose, we get 1 by n. 1 by n times that n by 1 is going to give us a 1 by 1 matrix, otherwise known as a scalar. Okay, so gx transpose times y. Okay, so why does this give us an inner product? When we're dealing with, we're just going to consider the case where we're dealing with real matrices. If we were dealing with complex matrices, we would need to do the adjoint there. So transpose, we would have the adjoint, the star, instead of the transpose. So remember, transpose means you take the complex conjugate. Okay. And actually, in that case, I would have to rewrite things a little bit. Okay. So why does this give us an inner product? Well, let's just think about some things. Is it symmetric? So if we look at the inner product of y and x, what are we going to get? We're going to get g y transpose y, x. But remember, for this transpose thing, this is equal to y transpose g transpose x. Okay, but we can write this as y transpose times, okay, we look over here, we could write G transpose times X as X transpose G. That is true, but let me just back up a second here and say the following. Since we're assuming that G is symmetric, G transpose is equal to G. And so this is equal to Y transpose times GX. And now, again, this is just the dot product. This is just another way to write the dot product of Y and G. So there's a number of ways that we can see what we can do. There's a number of ways that we can get to the next point right here. But one way is just to make that observation that this is just the dot product, and so this is going to be equal to GX transpose times Y. Like this. Now, if you're not quite convinced by that, that's fine. What we can do then is take the transpose and the transpose of that. And now what's going to happen here on the inside, when I do the transpose of this product, it's going to be GX. It's going to be the GX transpose times the transpose of Y transpose, which is just Y. And then we have the transpose around that. Okay, but this is a scalar, GX transpose times Y, okay? GX transpose is going to be a 1 by n matrix. This is an n by 1 matrix. So when we do this inside the parentheses here, we're going to get a 1 by 1 matrix. And so when we take the transpose of that, we just get itself. And so that's exactly equal to X. Okay, and then things like positive definite are going to imply that the inner product of X with itself is going to be greater than 0. Okay, and you can verify that an inner product defined this way for a symmetric positive definite, not just positive semi-definite, but a positive definite matrix is going to induce an inner product in this way. Okay, but what that doesn't prove the theorem that I have. That just proves that it kind of even makes sense to say. So what I need to show now is that given any inner product in Rn, it can be given as a dot product, Gx and Y. Gx, the dot product of Gx with Y for some, fixed positive definite or symmetric positive definite matrix. Okay, so how do I know that? So let's say let's have an inner product. Let's say that's an inner product. I'm going to define a matrix G. I'm going to tell you what its ij entries are. Maybe pause it and see if you can figure out what the ij entries are. So I'm going to define G via its entries. So I'm going to tell you. I'm going to sort of construct a matrix, and I'm going to tell you what its ij entry is. That is the entry in the ith row and j column. Okay. Well, this is just going to be equal to EI, EJ, where EI is the ith standard basis vector, and EJ is the jth standard basis vector. Like E1 is 1, 0, 0, 0, 0, 0, 0, 0, E2 is 0, 1, 0, 0, 0, 0, 0, so on and so forth. Okay, so my claim then is that this inner product is given in this way. Gx transpose Y. So in other words, my claim is this is equal to that. So I'm going to do a computation, and at the end of it, this, I'm going to say, is equal to that. Okay, well, let's just look at what's going on with this matrix vector multiplication. We have this matrix vector multiplication and then multiplying it by this vector as well that we're thinking about as being a matrix. Okay, so we can write this as a double sum. Maybe I'll sort of unpack this a little more slowly. We can write this as the sum. Sorry, let me make sure that I'm going to get the indices right here, because I want to sort of keep standard indices, I being the row and j being the column. Okay, so I can write this as the sum. Let me just write this. The sum j equals 1 to n. Okay, it's going to be the jth entry of this, the jth entry of g times x times the jth entry of y. Okay, so it's going to be gx is a matrix. It's going to be the jth entry of g times x times the jth entry of y. Okay, so let's think about what is going to happen over here. So what is g times x? Well, I think I'm probably going to have to come down over here. I'm going to have this outer sum, j equals 1 to n, and then in the inner sum, I equals 1 to n. What's going on with gx? Well, if I just look at this product, g times x, okay, I'm going to have the ith column of j times the ith entry of I. The ith column, the first column of g times the first entry of x. The second column of g times the second entry of x, and so on and so forth. And so if I unpack all of this, this is going to give me g ij times xi times yj, where xi is the ith entry of I, and yj is the jth entry of, sorry, that didn't need to have a vector error there. Okay. All right, so what can we do here? What is gij equal to? I'm just going to erase this. Gij is equal to eiej. So this is equal to eiej. Sorry, and then I need to do times xi, yj. Like this. Okay, now what I can do is I can move this xi into there and the yj into there. Like this. But now what I can do, I can use a linearity of the dot product and move this sum into there and that sum into there. Okay, what I'm going to get is the following when I do that. But all this is just writing x. Like this is just expanding x in the basis, in the standard basis. So this component here is x and this component here is y. And so this is equal to the inner product of x and y. Where again, remember the inner product here is the inner product that we're given, not the standard inner product. Okay, so that proves what I want to prove. So how does that have anything to do with what we're talking about now? Well, I need to show you what happens in the more general case. I want to get an equation like I got before when we're looking with the when we were dealing with the standard inner product. I had these this system of equations that I gave you. The M transpose MX is equal to M transpose B. I want to get something similar for this. Okay, So let's think about what this means. So if this dot product is equal to 0 for all columns of M, okay, what does this mean? It means if you do let me see where I want to put my parentheses. It means if you do G times B minus MX, okay, if we do the transpose of this times M, this is going to be equal to 0 for all columns of M. So again, this is a matrix. We're hitting it with a vector, or sorry, a matrix. Sorry, this is a vector. This in parentheses is a vector. We're multiplying it by a matrix. Matrix times vector gives a vector. We're doing the transpose. It's going to give us a row vector, and we're dotting it with in here. Okay, well, this being equal to 0, again, for the exact same reasons that we saw before, this being equal to 0 for all columns of M is the same as M transpose times this whole big thing, M transpose times G B minus MX. Wait, let me write this the other way. Right, so it's going to be M transpose times this vector is going to be equal to 0. Okay. M transpose times G, I think this is what I had. Is equal to the 0 vector. Okay, and why is that again? Well, this is just the standard dot product, right? And what do I do when you form this thing here? Well, the first row of M. So when you form this matrix vector product right here, what's happening? You're going to look at the this vector dotted with the first row of M. That has to be equal to 0. This vector dotted with the second row of M, that has to be equal to 0. All the way down to the very last row of M, the last row of M dotted with this vector has to be equal to 0. That's what it means when you say it's equal to the 0 vector. And the rows of M transpose are just the columns of M. So now we get the following equations that are similar to what we had before. It's going to be M transpose. Is going to be M transpose times G MX is going to equal M transpose G B. Notice that if G is equal to the identity matrix, this just reduces to the standard inner product case, and this equation right here just reduces to what we saw before. Okay, so that is it. Everything I've talked about so far this week has just been review of standard linear algebra facts, except for maybe this last part here where I talked about more standard inner products. That might not have been something that you exactly saw in previous linear algebra classes, but everything up to that, the orthogonal projections, this equation when G is equal to the identity matrix, that's all a very sort of standard thing that you've seen in your linear algebra class. I'm saying that not because if you don't remember it, I don't want you to feel bad or anything like that. I'm just trying to make sure that I can connect what we're doing now to things that you have seen in your previous linear algebra class.